Yeah, so maybe before I start to show some slides, maybe I will start with Blackboard. And I want to explain what is this conformal Yano-Killing tensor. What is the idea? So almost everybody in this audience knows what is the infinitesimal symmetry of the metric structure. Yeah? So usually people write some vector field X and take Lie derivative of this metric, and if it is 0, then we say that this is infinitesimal symmetry. If we pass to the, let's say, one form, yes, then it is this equation, or rather this tensor is equivalent to, up to some multiplication, to symmetric part of the nabla of this, let's call it K, nabla K. So it's a symmetric part. So in index notation, you have B mu, K mu symmetrized, yes? And then if you take to be 0, you say that this is a killing one form. If you say that the traceless part vanishes, that you say that this is conformal killing one form, etc. And then you can quickly, on this level, generalize this to higher rank tensors. So you put more indices here. And you play the same game. So for instance, what would be crucial in this talk would be something which I call Q. And this is a 2 form, has 2 indices, and then you take covariant derivative, you symmetrize, and then you write that this is, let's say, proportional to the metric plus extra terms which are built from W and G. So, and this is the conformal generalization of so-called Yano. So Yano means that this, so Yano is that this is 0. Okay. So some people call this kind of objects hidden symmetries. So let me start with some slides. How it works. Okay, so let's try it. Okay, so there are some points here how those objects appear in GR, and maybe I will not read even this because I have not so much time, but let me say that a problem of asymptotic flatness is a well-known problem. People try to attack with killing vectors, but I think that those conformal Yano-Killing tensors are better for this kind of question. Yeah, you can define some conserved quantities. You will see in a moment how it works. So you can ask where those objects appear as an asymptotic symmetry, but precise exact symmetry. So of course in Minkowski. In Minkowski, those tensors in Cartesian coordinates have components which are quadratic polynomials. But I think that in the sitter, which is conformally related to Minkowski, it is much simpler. So the construction of solutions with cosmological constants is much simpler than in Minkowski, and then you can pass because of conformal covariance of the solutions of this equation, etc. So the main application which was made many years ago, and is so-called Carter constant, is just type D spacetime like Kerr. So Kerr is already discussed. Maybe I managed also to show you some tau NUT but Euclidean, where dual mass equals to the usual mass. This dual mass is this L parameter in the previous talk. So let's go on. So other applications. So Yeah, so symmetries, I will not discuss all these applications. Maybe I will show you Fokker-Elipser equation. This is a problem how to describe Maxwell equations in a simple way as a one equation on Kerr background. So yeah, spin one field in Kerr spacetime. In terms of conformal Yano, it's a very natural construction. Maybe I managed to say something about unconstrained degrees of freedom for linearized gravity, but I'm not sure. Constant of motion and geodesics. So this is related to the following phenomena. Once you have a solution which is a two-form, so skew-symmetric tensor, you may contract it with one index with itself, so you can take a square, and then it will be a symmetric object, and it is called conformal symmetric killing tensor. So roughly those Qs are square roots of well-known symmetric killing tensors. And in fact, this Carter constant needs this symmetric one. So maybe I managed to show you more details. And the very recent application, which I learned a week ago, is that in this type D spacetimes which admit conformal Yano, this tensor helps to construct round spheres. So there's a problem on how to construct round spheres in space-time and how many of them exist, etc. Okay, so this is the beginning. Let me tell you in a few words about more detailed. So I will show you several equivalent forms of the equation, and it does not work. Where is this? Where is this computer? Okay, now it is fine. So I'm repeating on the slides in a more detailed way what I said on a blackboard. So you see, this is the conformal Yano tensor where there is this right-hand side. When this is 0, it's Yano. So this is the moment of, okay, how much time I have? So I should be more. Okay, so it is also crucial for asymptotic constructions to consider three-index tensor, which is just the equation. Yes? And the properties of this green three-index tensor at infinity control somehow space-time in a nice way, and then you can say, what does it mean, strong asymptotic flatness? What is the relation between symmetries in terms of killing, asymptotic killing vectors in anti-de Sitter and conformal Yanos, etc. So you may write definition of conformal Yano in such a way that this tensor vanishes. Yes. Okay. So some properties. There is one more abstract way to write this equation, which is general for any p form, not only for a two form. So for some of you more mathematical side, it is a kernel of the twistor operator. Okay. So this is the law which says that this object has some properties with respect to conformal rescaling, and you know, once you prove this you have the theorem. Yes. So the transformation law between G gives transformation law for conformal Yanos, and here is its explicit form of symmetric conformal killing tensors. And again, we have nomenclature killing or conformal killing. Okay. So the main theorem says that somehow Q is more. Say it in English. Okay. So anyway, this symmetric A is a square of Q, and in fact you can even build something similar, as you see in a moment, from two different skew-symmetric conformal Yanos, also some symmetric. Okay, so these are just formal properties, mathematical. There are more of them. For instance, there is nice conformal equation, which I can tell tensorial Klein-Gordon equation for this two-form. And I guess here we are restricted to dimension 4, and let's put n. Don't forget about general. Yeah, there is problem of potentials, but it is not interesting now. So okay, so in fact the divergence of conformal Yano produces Killing vector, but you know, sometimes it is 0, which means that this is Yano, and this is the property for Kerr, for instance. As you see that some tensor has divergence which is symmetry, and other divergence is just zeros. Okay, so for how to say, this is not physical. This is not physical because we assume that M is compact and this is Riemannian structure. However, in this case, because there is no boundary, we have a nice property that this overdetermined system of equations for Q reduces to one equation. So it's some Klein-Gordon equation, and it is nice to know this. And okay, so the next property, a lot of time. So the next property which is crucial in dimension 4 is that the Hodge dual of two-form is a two-form, and it is also a conformal Yano. So this is another story. Okay, so now let's start with some basic application. So suppose we have a spin to field. I write this in an so spin to field abstractly means that we have some algebraic properties which are well known for the Weyl tensor. And but you know, you may think about given background and some linearized Weyl as well, so linearized gravity. And then you have star operation for first pair of the indices or second pair of the indices, and there are some nice properties with these stars, and also if you do this for general length and metric in a proper way, you have the same formula. Okay, so Bianchi identities plays a role for this as a field equation, you know. So one can say that 6 is a spin to field equation. They are equivalent to other ones, and one should remember that Scouten tensor has to vanish to fulfill this equation in the case of full linear field. So okay, and now we play the game. So we take this file, we contract with Q, and we want to have something which produces a divergence-free by vector density, or if you take a Hodge dual, it would be just closed two-form. So there are both possibilities. Anyway, once you integrate, you try to produce from this two-form a Gauss law like in usual electromagnetic case, and you assume that it has to be 0, you end up with the observation that whenever W is a spin to field and Q is a conformal Yano, which means that the right-hand side in 7 vanishes, then you produce some, let's say, gravitational charge, which is electromagnetic analog. And then you can play the game further. So whenever you have this spin to field and this conformal Yano, it is not only that this integral has something to do with Gauss law, but you can reconstruct the full Maxwell equation. So contraction of spin to field with conformal Yano gives Maxwell field. Not physical one, just a Maxwell field. And then you can play the game two different ways. You take two surface integrals, so you treat these closed two forms in a proper way. So you have this electric and magnetic charge analog. Or you try to produce energy momentum tensor, and then you have some conserved current on a codimension 1 hypersurface. So, no, conserved current is in space-time, but if you want to integrate this conserved current, you produce some conserved quantity like Hamiltonian, you know, just on a codimension 1 surface, yes? So this is nice, I guess. You can. So let me comment also that this left row, this left column is linear in terms of the Weyl. However, the right column is quadratic in terms of the Weyl. And this right-hand side often are called super energy tensors. Yes?
So this spin to field, it is also traceless?
Yes.
Straight.
Yes. So these are details. So this is the theorem which I already mentioned, and then we can pass to solutions. Okay, so this is explicit general solution in Minkowski in Cartesian coordinates, so quadratic polynomials, as I told you. These two, yeah, you can think about two forms, but you have a matrix, so you can think about bivectors, doesn't matter. So what is nice about this is that to construct the full space of solutions, we need only similarity transformations. Those conformal accelerations are not needed. So from those generators, translations, Lorentz transformation and dilation, you can construct by wedge product, etc. They're all solutions. Okay. So maybe I will skip something. So maybe you should remember that the dimension of space of solutions is 20-dimensional, and this is the general for p-forms, etc. So this holds for maximally symmetric spacetimes, let's say. And because of this conformal transformation, we have 20 Minkowski, de Sitter and de Sitter. Okay. And there is some physical motivation to say now about these electromagnetic charges. So for instance, this dilation times translation by vector corresponds to the linear for momentum. And the dual object is so-called dual for momentum. The time component in D is just this dual mass, but there is also spatial part, which is in Demiański-Bebański solution. So all these parameters are somehow included. There is this angular momentum, which is obvious. For Kerr is this n times a parameter, yes. But there are some other objects which usually vanish. For usual solutions which are asymptotically flat, they vanish. So these are these accelerations. But on this, maybe 20 minutes ago, appeared this parameter alpha in this accelerated tau, NUT, etc. So all these parameters have So this parameter alpha has something to do with this W. Okay, so I'm saying always that this is something which corresponds, because these are 6 numbers. Yeah, this is skew-symmetric tensor. There are accelerations and angular accelerations, altogether 6. So yeah, but they are usually not 6. Okay, so the second row on this picture was that we can build something like that. The last line. So this is obvious, but when we put instead of F this W contracted with Q, some people say that this is queer tensor because it's not normal. Yes? It's peculiar. Yeah? And this is why Q. Okay. So one can build 6-index tensor, which is upper to the Bell-Robinson. So let me say that there is some quadratic formula in terms of spin to field, which builds some 6-index tensor. It has some properties. So firstly, indices are symmetric, and there are skew-symmetric pairs, and then the main property is that, first of all, the trace of this tensor has something to do with Bell-Robinson. Moreover, we have some divergence property and some algebraic property. There was a name Ektem which discovered this tensor in elasticity. So it's different physics. However, the main theorem is that we have conserved current. So whenever we have spin to field, we build this T, and then we contract with a conformal vector field and 2 different, maybe, conformal Yanos, and we have conserved current. And then when we integrate on T equal constant size, we get some number, which is conserved in time. So you may easily control initial data. So because those P and Qs are big at infinity, it helps to control in a better way some initial data, and then you can prove some stability or whatever. In fact, these methods were used, maybe not in this language, by Christodoulou Kleinerman and other people, you know, this Rodnianski, etc. Anyway, okay, so now 5 minutes?
2 minutes cover and then 5 questions or maybe
But then there is a coffee break, yeah? So, okay.
Well,
so
that would be fluent.
So, okay. So you see, Kerr spacetime is obvious. It was shown many times. So what is new is Yano for Kerr. So we have this explicit form of Yano. We have maybe asymptotics. It's not. We have dual object, which is no longer Yano. It is conformal Yano.
This is, I think, Lane, Houston, and Somers found Yano for Kerr.
Yeah, I know.
But you said it's new.
No, it is the same old stuff. No, it's the same old stuff. No, don't worry. So, and the observation that this conformal Yano is a potential for time translations, you know, for this symmetry. Okay, and what is maybe less known is Euclidean NUT matrix, which is self-dual. So this is we have many of them. So we have many Yano tensors, in fact 4 of them, and we have those 3 while I are self-dual. So there is nothing new, but there is, so altogether we have 5. Okay, and then we can play the same game, and we can check something. Maybe this is not important now, so forget it. And then we can pass to symmetric killing tensors, and this will be the end of my talk because I should finish. So in case of Kerr, we have 3 of them, but only one of them is killing tensor, and 2 of them are conformal killing, and those conformal killing are good for producing conserved quantities and null geodesics. So there are some explicit forms. This is how constant of motion appears in along geodesics. This is obvious. So this is k mu nu, k p mu p nu. Is this constant of motion? And then for this top knot, you can produce more general symmetric, which is product of 2 different, and then you have 5 of them, so you have 5 by 5 matrix of such tensors, and then you have several components which are non-vanishing, you see. At the end you have 10 of them. So in self-dual tau-knot Euclidean you have 10 symmetric killing tensors. And 5 of them are killing, and 5 of them are conformal killing. And that's it. So this is, I can continue if you like, but not now. And maybe, yeah, I will finish with this slide. Okay, thank you very much.
Questions? The natural question would be, what is the most important thing that you wanted to tell, but you didn't have time for it?
Well, difficult question. But maybe I will tell about linearized gravity. So you see, you have noticed that W contracted with Q gives Maxwell, yes? But you can contract Maxwell again with conformal Yano. Then you produce scalar. And then, for instance, in the Kerr metric, where you have only Q and star Q, you can produce complex combination which corresponds to the killing spinor. And then this contraction gives you a complex scalar function, and this is exactly the function which describes all degrees of freedom of gravitational waves in Minkowski spacetime, and you can show that all other components of the Weyl are expressed in terms of this field. The same happens for Maxwell field on Kerr spacetime. You can contract Maxwell auxiliary field with Q. You produce with Q times I star Q. So F mu plus I star Q mu. This is certain scalar psi, and then you quickly check that this scalar psi fulfills Klein-Gordon equation with complex potential, which is known in literature Fokker-ellipse. And it contains all data of electromagnetic waves. So you see, in some sense, linearized gravity, spin 2 field, and spin 1 field can be described with those objects, at least on some space-times, not whenever we have this conformal Yano. Okay, so let me finish.
Okay, thank you very much.